Everybody, last two bullet points for video notes 13.2 and last video notes of the year. So just gonna give a shout out to my homies Megan, Anna, and Mattis who drew me a swagalicious pic on my board today. You guys rock. And this is a shout out to everybody in first hour and second hour. Whether I say your name or don't say your name, I'm thinking of every single one of you right now. Peace. Alright, here we go. Please read chapter 25 still. There's two sections that I'm going to cover in this video notes. Hey, you get an automatic 10 out of 10 if you read the section and answer the 5 key concept questions from the guide for reading in your notes. Make sure to put the questions and answer in your notes to get your 10 out of 10 automatically. Wow, fun times. All right, here we go. Fusion and fission. Hey, I want you to know that fuse comes together. Fuse together. All right, so there's only one S in fusion because it came together to make one S. Two smaller particles collide. Nuclear particles, two small nuclei collide and make a larger, heavier particle. Usually some neutrons are also made, and it gives off a lot of energy. Okay, fission is the opposite in terms of what happens. Fission aparts, fission splits. So look at those two S's. We got to split the S's in fission. Right? A neutron usually is the trigger. The neutron hits the target. The target is a big nucleus. All right, hits a big nucleus and makes smaller particles. When it makes those smaller particles, it also releases a bunch of neutrons and some energy. Okay, so here's two pictures down here. I want you to decide which one's fission and which one's fusion. All right, for fusion, look for something bigger coming out at the end than the start, and for fission, look for something smaller coming out. Okay, so fission and fusion facts. Fusion is a hard process to start because you gotta get these two tiny positive things together, but positive things repel each other. So fusion is hard to start. Fission, on the other hand, is easier to start because you just got to hit it with a neutron. Neutrons have no repulsions, and so they're good bullets to cause a big nuclei to split. So where do we use fission? Fission is the nuclear energy produced in that produces our energy. The nuclear process that produces our energy in a nuclear power plant. Also, fission can be used for bombs. Fusion is the nuclear process that gives us pretty much everything we have in terms of the sun is our big mass of incandescent gas, a giant nuclear furnace. All right. So fusion is what happens in the sun. So all of the energy we get comes originally from the sun. Okay. You can do a fission to fusion bomb where it starts out, the trigger of the bomb is a fission trigger, but then it causes fusion to happen. So fusion is in the sun. We at this point don't have any means to control it, so we can't use it for nuclear power. Fission happens in fission bombs and in nuclear power plants. All right, so fission. What really happens is a neutron hits a big nucleus and it splits into smaller nuclei and some neutrons. It can cause a chain reaction because if you have one nucleus and it splits, then you make some more, but then all of those particles, the neutrons, could hit more big nuclei and split, and so on and so on. So you might be wondering what a chain reaction looks like. Here's a model of it. You should draw this. So first neutron hits big nucleus. Neutrons produced. Those neutrons hit big nucleus. More neutrons produced, hit more big nuclei, and so on and so on. So you get this whole chain reaction, and it produces a lot of energy. That energy gets out of control, and that's why you have an explosion. But guess what? Nuclear power is used in nuclear power plants where we use this fission, but it's controlled. All right. So the reason we use fission is it generates a lot of energy, like lots more energy than burning coal. And it's easier to start than a fusion reaction, and it's easier to control than a fusion reaction. So fission is used in power plants. Fission is the splitting, and it's used in power plants. It provides a large amount of energy. And guess what? No excess carbon dioxide, no excess sulfur dioxide, so there's no greenhouse gases, no acid anhydrides to cause acid rain, no carbon dioxide to have the global warming effect. So that's some of the reasons that it's good. Large amount of energy, no greenhouse gases. What? Nuclear power is bad? Who said that? I did, because there's some drawbacks to it. Nuclear waste has to be stored away from people because it's radioactive for years and 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 years. All right, nuclear waste must be transported through public places. They have arguments about, like, that train's not coming through my town with your nuclear waste, and I'm not storing that in the mountain next to me. Also, nuclear power plants, there could be accidents. This is like a pool of water where spent nuclear material is stored. What happened in the Japan when they had the tsunami is that the water in these leaked out, and so this nuclear waste was not covered with the water, and they had a lot of issues with that. All right, so when we talk about nuclear stuff, we also have to talk about what's called half-life. Remember this spontaneous radioactive decay, alpha, beta, gamma, yada. We can't control it, we can't speed it up, can't slow it down, but we got to understand it. So all things that decay through a spontaneous nuclear process have been measured to see what their half-life is, okay? Excuse me, half-life. So in you and in plants, there's a constant ratio of one isotope of carbon in comparison to other isotopes of carbon. So the ratio of carbon-14 to carbon-12 in living things is a constant ratio because we're always taking in, we're breathing out more carbon dioxide. The ratio of this is always the same because we're renewing our carbon supply as we live. But as soon as you die, then this ratio, we're not taking any more carbon-14 or carbon-12 in, and the carbon-14 starts to decay, so the amount of carbon-14 to carbon-12 goes down. All right, so we can tell by something that's been, we can find out how old bodies are, how old clothing is, how old houses are, talk about why in class, but because these used to be living things, we can figure out how old they were by using a process called half-life to determine. Okay, so we can apply half-life to certain kinds of problems. All right, half-life is a time. Half-life is a time. Make sure when someone says, hey, what's the half-life? Make sure they're telling you in hours, minutes, days, years, centuries, whatever. Half-life is a time. Okay, so the half-life for zirconium-84 is 26 minutes. Hey, there's our time. I'm going to put T1 half because that's the half-life. If you start with a 175 gram sample, so this is our start mass, okay, how much will be left over after 104 minutes? This is total time, right? Total time. So how do we figure out this problem? What is it that we're trying to find? How much left? Find end mass. How much is left? So if we're starting with 175, we'll have less than 175 when we're done. We got to figure out how much less. So I know that the total time is 104 minutes. I know that every 26 minutes, a sample of zirconium, half of it radioactively decays, so I only have half left. So I find out that in that 104 minutes, 4 half-lives go by. I divide it. 4 half-lives go by. So what does that mean? It means we're done? No, because the answer to that question is how much will be there. If I'm starting with 175 grams, then after 1 half-life, there will be 175 divided by 2 grams left. So 175 divided by 2 is 87.5 grams left. But that was only after 1 half-life. After the next half-life, that divides by 2. So we have 43.75 grams left. That's after 2 half-lives. How many times am I going to cut this in half? I'm going to cut it in half 4 times because that's how many half-lives it went through. So we're going to get 221.875 grams after 3 half-lives. That divided by 2 is going to be 10.94 grams left. All right, so after 4 half-lives, there will be 10.94 grams left. None of these problems have a simple way to solve them, but they are all simple ways to solve. I know that doesn't make sense, but you have to just think about what's happening. So in this one, it tells you half-life, T1 half, is 12 days. How many grams remain after 72 days when the initial amount was 20 grams? So this is start grams. That's how many grams we're starting with. And how many grams are find end mass. End mass. All right, so we got to figure out in that 72 days total, every 12 days, what happens to our sample? Well, it radioactively decays to half its original mass. So that means that it's going to do that 6 times. 6 half-lives happen. So what do? I take, well, my 20 gram start, divide it in half. 1, 2, 3, 4, 5, 6. After I do all that, I find out that there will only be 0.3125 grams of barium-131 left after 72 days. Okay, so find out what it is you're looking for, find out what you know, and then think it through. Okay, so hey, we can calculate the half-life of something. So if we had 100 grams of carbon-14 when we started, but only 25 grams of carbon-14 left after this total time, what is the half-life? Okay, so this is total time. This is start mass. This is end mass. Okay, so how did the 100 grams turn into 25? Well, the only thing that could happen to mass in the half-life part is it could cut in half. So it went from 10 grams to 50 grams. Then it went from 50 grams to 25 grams. Hey, how many times did it cut in half? Well, it cut in half twice to get to 25 grams. So this sample goes through 2 half-lives. So how do we know how long a half-life is? Well, it took 11,460 days to go through 2 half-lives. So that means each half-life was 5,730 years. I said days. Harbin, come on, this is years. All right. All right, so that means that whatever this sample was took this long to decay. So every half-life was 5,730 years. Okay, we're starting with 50 grams start mass, and it turns into 3. That's the end mass. In 75 days, that's a total time. What are we trying to find here? Half-life. All right, find T1 half. So, well, if we take 50 grams and cut it in half, we get 25 grams. Not yet. Cut in half again, we get 12.5 grams. Oh, still not others. Divided by 2 is 6.25 grams. Here we go. We cut that in half, we get the 3.13 grams. Alright, so that means our sample to get from 50 to 3.13 grams cut in half 1, 2, 3, 4 times. So it went through 4 half-lives in 75 days. So in 75 days, went through 4 half-lives. That means each half-life was 18.75 days. That's how long the half-life equals the half-life. Alright? Alright, let's see what's going on. These are, you saw really 2 basic kinds of half-life problems. Looking for final mass, looking for half-life. There are other ones we'll practice in class. So anyway, uses of radiation. Other things you have to know. You can use radiation to brain image. You can use radiation to date old things. Not that you have to date old things, but you can tell how old things are. They use radiation in power plants. That's the fission. You can tell if something's leaking by detecting radiation. You can measure the thickness of plastic wraps and foil. So they use radiation. They shoot it through at the plant to see if it's the right thickness. Depending on how much goes through, tells you how thick your foil is, how thick your plastic wrap is. Radiation, as you know, can be used in cancer treatment. You can use radiation to build smoke detectors. You can use radiation to keep food fresh for longer. So all of those are uses of radiation. Alright, so let's review and play some music. Alright, you should know that nuclear power has been seen as good and bad, and you should have some reasons. Fission splits, fusion comes together, okay? And so it sticks. For half-life, if it's mass, okay, keep cutting it in half if it's the mass, and then figure out how to solve the problems. We'll practice. Make sure you know some things that radiation is used for. Alright? So anyway, guys, this is it. Hopefully you read chapter 25. I gave you a way to get an automatic 10 out of 10 on this quiz. I'd say take it. Alright? Make sure you can do these 2 bullet points, and you've got oh, here, we gotta make sure you know some of that as well. Alright? So, hey, it's been fun. I want you to have a great life. Hopefully see me next year when you're at North Campus once in a while. This is for everybody. Even if I don't say your name, I am totally giving you a shout out. Shout out for chemistry and for y'all. Peace out. It's been a great year, and I hope you guys all have a beautiful day. From Harbin.